Now let's turn our attention to parametric equations and their graphs.
Generally, you have y as a function of x. But of course, we have seen that not every equation has y as a function of x. For example, you can have something like x is equal to y squared. And here, this is no longer a function of x. And you can see that even from the graph. You take the equation y equals x squared and graph it, that is a sideways problem, which, since it does not pass the vertical line test, you learn in college algebra that this does not express y as a function of x. However, you can, of course, express x as a function of y, because here, if you simply flip that on its side, that does look like a function now, even though now we don't have y as a function of x, but rather x as a function of y. However, there are going to be some graphs where even that won't work. For example, if you have something like x squared plus y squared equals to 1, that graphs as the unit circle, which of course is not a function no matter which way you turn it. You don't have x as a function of y or y as a function of x or really anything else, because no matter which way you rotate, you always have the exact same object, the circle. And yet, we have expressed the points on the unit circle using functions. That's how we define the trigonometric functions, or at least that's one way to define them. Because if I have an angle theta, then this point can be thought of as not one function of the angle theta, but two functions. After all, the x-coordinate can be thought of as the cosine of that angle theta, and the y-coordinate can be thought of as the sine of that angle theta. So yes, it's true, this is not a function of where x is a function of y or y is a function of x, because it fails a vertical line test or even a horizontal line test. But you can still express this with a function so long as you don't consider x as a function of y or y as a function of x, but rather both x and y as functions of a third variable, in this case theta. This is an example of what's called a parameterization. A parameterization is treating the x and the y not as functions of each other, but as functions of some other variable called the parameter. So let's formally define what we mean. Here, definition, let's begin with a couple of functions. Let f and g be functions of some variable which we'll call t. We can use theta, we can use w, any letter we like. However, t is a fairly traditional variable for these functions. Let f and g be functions of some variable t, where t is on an interval I. Then the equations, x equals to f of t and y equals to g of t, are called parametric equations. With t as the parameter. Right, so these two equations are your parametric equations, and t is the parameter of the parametric equations. If you then take the collection of all x's and y's together and graph that, that's called a plane curve. The collection of all points of the form x comma y, or you can also say f of t comma g of t, but it's usually simpler to just say x and y, is a plane curve. A curve on the plane. Note that that means that even though the two variables may not be functions of each other, they are each considered a function of some third variable called the parameter. So let's now consider an example of this. Let's go ahead and graph the plane curve that is given by the parametric equations. Where x is equal to the square root of t, so that's the function of t that gives you your x value, and y is equal to t minus 1, where t is any positive number. Note that sometimes your plane curve must restrict the values of the parameters, because otherwise your expression would either be undefined or defined in a way that we do not wish to use. For example, if our parametric equation was something like 1 over t, well then we couldn't define for t equals to 0, because you can't divide by 0. At that point you may wish to say, oh, I want any number other than 0. Or in some cases, depending on what this one is, you might say, well, I only want numbers greater than 0. Or I only want numbers less than 0. In this case, we do not wish to define this for t as a negative, because the square root of a negative value, of course, is a complex number, and that is not something we're about to start graphing. We're trying to graph things on the xy plane, which means we need everything to be real. All right? So let's go ahead and graph this. There are a few ways to graph a plane curve. For right now, we're going to stick with the simplest one, and that's simple substitution. Here, I'm going to take values of t that are greater than or equal to 0 and just plug them in. Okay. Let me start with just 0, and let's see what we get. If we take t is equal to 0, then x equals the square root of 0, which is just 0. And y is equal to 0 minus 1, which is negative 1. Okay. If t is equal to 1, well then x is the square root of 1, which is still 1. And y is equal to 1 minus 1, which is 0. Notice all I'm doing is plugging in my numbers. Here, I could say t is equal to 2, but then I'd have to take the square root of 2, which, yeah, I can do that, but you know what? Since I'm free to choose what numbers I'm plugging in, let me choose a number that's easy to take the square root of. I'm going to use the number 4. 4, take the square root of that, that's 2. So that'll give me my x value. And then my y value will be 4 minus 1, which is 3. And then I'll do one more. I'll say t is equal to 9. Okay, the square root of 9 is 3. And then 9 minus 1 is 8. Now here, t can be any number greater than 0, so of course this would keep going. But here, just like any other graph, like if you were graphing a line or a parabola, you wouldn't find, you wouldn't keep going. You'd have just enough points to start to see your pattern and then graph that. All right, so here we go. We're graphing on the xy plane. Notice that on the xy plane, there is nowhere to put t. There's a place to put x and there's a place to put y. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So these are ordered pairs. We're not going to worry about t. 0, comma, negative 1. Okay, well, that's my starting point. X is equal to 0, y is negative 1. And then 1, 0. That's that point there. And then 2, 3. 2 to the right, up by 3. And then 3, 8. That's 3 to the right, up by 8. Like that. And if you connect your dots, you get a pattern that looks something like this. Kind of looks parabolic. Note that here we have x's and y's giving us our location on the xy plane as usual. But then you say, well, what about t? Do we just not use these anymore? So here we're going to label each point with its corresponding t value. Here t is equal to 0. Here's where t is equal to 1. Here's where t is equal to 4. Here's where t is equal to 9. The reason we use the letter t is because often this represents time. Here we're looking at 3 dimensions, 2 spatial dimensions, how far left and right you are, how far up or down you are, but we're looking at a temporal dimension as well. In other words, at what time am I at these different points? Oh, well, when time is equal to 0, when I got started, I was here. After 1 unit of time, 1 second, 1 minute, 1 hour, whatever, I'm here. After 4 units of time, I'm there. And after 9 units of time, I'm there. So one thing that a set of parametric equations does, one thing that we can have with a plane curve that we don't usually have with other graphs, is a concept of orientation. In other words, this has a direction. This isn't just this collection of points. It's the collection of points that start from here and move up and to the right. There's a direction. You may have different plane curves that travel along the same path, but if they go in the opposite direction of each other, they are not considered the same curve. If I had this exact same curve, but instead of going from the lower left to the upper right, if I went from the upper right down to the lower left, that would not be considered the same plane curve anymore. It's not just the curve, but also the direction over which you travel through that curve. And the way we indicate that is with these arrows. These arrows are not just decorative, they are a part of the graph. They show you the orientation, which direction you're traveling in. So go ahead and give this a try. Using just some simple substitution, you're going to plug in some points. You can plug in just sequential numbers 0, 1, 2, 3, 4, 5, or you can do like I did and maybe choose numbers that are a little more convenient. It doesn't matter what you choose as long as you're in keeping with your parametric equations and as long as you are not using a value of t that's not allowed. Go ahead and graph this by substitution. Let's graph x equals t squared plus 1 and y equals t cubed minus 1. Here we're not given any restrictions on t, which means that you can use any value of t. Here, in fact, let me actually just write this. Let's say t is simply all real numbers bound between infinity and negative infinity. If ever you're told this, that means you can use any value of t, or if you're not told anything, that means the same thing. You're assuming you can plug in any value of t. But here, let me explicitly state it. T is anything between minus infinity and infinity. Right? You might wish to actually have a few negative numbers that you plug in just to see what happens on the negative side. So maybe -2, -1, 0, whatever you choose, whatever's convenient. Go ahead and pause the video, give this a try, find your appropriate points, and graph including any orientation that your graph has. All right, so let's go ahead and give this a try. We're plugging in values of t to find values of x and y. Here it doesn't look like I have any problems plugging in any small regular numbers. I wouldn't want to plug in something like 10 because I'm going to cube it and that's going to get really big and difficult to graph. So let me stick with small, simple numbers like -2, -1, 0, 1, and 2. Just like that. So if I plug in -2, that's going to give me -2 squared is +4 plus 1 is 5. -2 to the third, that's -8, minus 1 is -9. -1 squared is 1, plus 1 is 2. -1 to the third power is -1. -1 minus 1 is -2. Okay? If I plug in 0, well, that's just going to give me 1. And if I plug in 0 here, that'll just give me -1. Okay? If I plug in 1 right here, 1 squared is 1, plus 1 is 2. And if I plug in 1 right here, 1 to the third is still 1, minus 1 will be 0. And finally, if I plug in 2 right here, 2 squared is 4, plus 1 makes 5. Over here, 2 to the third is 8, minus 1 makes 7. And this does keep going forever in both directions, as we see here, but that should be sufficient to give us a pattern so that we can form a graph. All right, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. We don't worry about these for now. Only X and Y are telling us the location of our points. These are going to help us find our orientation at the end. So our points are 5, negative 9. 5 to the right, 1, 2, 3, 4, 5, and then 9 down. Right about there. 2, negative 2 would be 2 to the right and 2 down. 1, negative 1 is 1 to the right, 1 down. 2, 0 is 2 to the right and then don't go up or down at all, like that. And then 5, 7 would be 5 to the right and then up by 7. Okay. If this is not sufficient for you to see what that looks like, you may wish to plug in a few other points. Nothing stops you from plugging in a half, a third, 1.6, or whatever. However, this is sufficient for me to see that this bends this way and bends this way. Notice that your x value will always be 1 or greater, because after all, if you square any number, you get a positive plus 1. So the smallest this can ever be is going to be 0, which means the smallest x can ever be will be 0 plus 1. Okay, so x will never get any less than 1. That's how I know it wouldn't continue back this way. It's going to come to here and then over here. Here, let's go ahead and label our t values. T was equal to negative 2 over here. At 5, negative 9, we have t is equal to negative 2. And over here, t is equal to negative 1. Here at this cusp, you have t is equal to 0. And then at this point, t is equal to positive 1. And then t is equal to positive 2. And so notice our orientation. As t increases, you go up toward your cusp. And then once you hit your cusp, you're going to go up and away this way. Note that your orientation would be different if you had a curve that went from the top down, or it would be different even if you had something that started from the cusp and went this way and this way simultaneously. Having yourself go through these points in a different direction would lead to a different plane curve. So here, these orientations are part of the graph. If these are missing, or if they are incorrect, you don't have the correct graph. Now, that is not the only way that we can graph a plane curve given by parametric equations. This is one way, and it's fairly simple, but it can be a little tedious and a little imprecise, especially as these get more complicated. Another way in which we can graph these is by eliminating the parameters. So let's consider an example of this. Example, we're going to graph, but instead of doing it point-wise, we're going to graph by eliminating the parameter. For example, we're going to take x equals t minus 2 and y equals to t squared. Okay? Now here we're not told any restriction on t, which means that if we're not told any restriction on t, we can use any value of t. So here t is any real number from negative infinity to infinity. Now of course one thing we can do is we can start plugging in values of t, negative 2, negative 1, 0, 1, 2, and so forth. Another thing you can do is the following. Take one of your equations, it doesn't really matter which one, and solve for the parameter. Here, if I solve for t, I'm going to have to take a square root, which will give me a plus or a minus. And plus or minus might be a little bit rough to work with. Over here, to solve for t, all I have to do is add 2. Okay, so since I'm free of choosing which one I want to use, I think I'd rather avoid plus or minus a square root. I think I'd rather just add the number 2. That sounds easier to do. So right here, I can take this equation and simply adding 2 to the other side, I get that t is equal to x plus 2. Add the 2 over. But now, if t is equal to x plus 2, that means that the t over here in this parameterization, in this parametric equation rather, can be replaced by x plus 2. So instead of saying y is equal to t squared, you can now say y is equal to x plus 2 squared. And now we can graph that. If you want, you can always expand this. You can always write this as y equals x squared plus 4x plus 4. But actually, this one's a little bit easier to graph, because if you think back to your college algebra, x squared is a parabola that faces up toward the positive half of the y-axis. By adding 2 on the inside of your function, you're moving everything to the left by 2. You may remember, if you have f of x is a graph, f of x plus a number moves everything to the right, it moves everything to the left by c units. And if you have f of x minus c, it moves everything to the right by c units. If your plus c is on the outside of the function, that moves everything up. And if you have minus c on the outside, that moves everything down. So here, that's plus 2 on the inside of my function, so it moves everything to the left. So I can now graph that without having to plot individual points. It's a parabola that's shifted over to the left. So it's a parabola. Normally a parabola would start at the origin and go up this way, but because of that plus 2, we're going to move everything to the left 2 steps. So the vertex should be 2 steps over this way. So really we have this parabola over here. All right, but what about my orientation? Do I don't need to worry about that anymore? I mean, there's no more parameter. Well, no. This equation gives you the path. It tells you all the points that these parametric equations would also give you, but it doesn't say anything about orientation. So the last thing we need to do now is we need to establish our orientation. Simplest way to do that is to just pick 2 sequential values of t and plug them in. So here, instead of plotting a lot of points to create a graph, I already have my graph. I just need 2 points to give me my orientation. So let me just use 0 and 1. If t is equal to 0, okay, well then x is 0 minus 2, that's negative 2. And y is equal to 0 squared, which is still 0. Okay, so negative 2, 0, that's right there. That's what happens when t is equal to 0. If I plug in 1, 1 minus 2 is negative 1 for my x value, and 1 squared is positive 1 for my y value. So negative 1, 1, that's what happens when t is equal to 1. And there we go. Now I know my orientation. My graph goes from here this way. So my parabola has this orientation, starting from the left and going to the right. Your elimination of a parameter gives you the collection of points. That doesn't mean we are now safe and free to, it is now safe or free to ignore the orientation. It just means we now have our path. We still need to label our orientation. Another example of this is, note that this, where we isolate one variable and then plug it into the other equation, will often work. However, there is sometimes an easier alternative if your parametrics involve trigonometric functions. Because after all, trigonometric functions have identities that relate one to another. So for example, we might consider something like this. Let's say x is equal to, I guess I should give directions to this, right? Let's go ahead and graph by eliminating the parameters. Oh, I don't know how to spell. Let's try that again. Eliminating, there we go. Eliminating the parameter. All right. Let's say x is equal to -1 plus 2 times the cosine of t, and y is equal to 1 plus 2 times the sine of t. And here they give us a restriction on t. T is bound between 0 and 2 pi. All right, so let's go and give this a try. We're going to begin by isolating not the parameter, but the trigonometric expression of the parameter. In other words, don't get t by itself, get cosine of t by itself. Over here, don't get t by itself, get sine of t by itself. You'll see why here in just a moment. All right, well, we start by adding 1 to this side and then divide by 2. So we get that the cosine of t is equal to x plus 1 divided by 2. And over here, we can subtract the 1 and divide by 2. So we get that the sine of t is equal to y minus 1 over 2. Okay, so now what? Well, normally we would now say, okay, plug one into the other. But notice if I isolated t here, that would give me the inverse cosine, the arc cosine of x plus 1 over 2. And since that's what t is, you would now have the sine of the arc cosine of x plus 1 over 2. Which, yeah, we can do that. We know how to deal with compositions of functions and inverse functions. But that just seems complicated, doesn't it? It's much simpler if you recognize the Pythagorean identity that you can now build. Here, square both sides. Cosine of t squared is equal to x plus 1 squared over 2 squared, which I think I'll just write as 4. Over here, I can write sine squared of t is equal to y minus 1 squared over 2 squared, which again I think I'll write as 4. But now notice, the Pythagorean identity is that the cosine squared of t plus the sine squared of t is equal to 1. Oh, but I can replace cosine squared of t with x plus 1 squared over 4. And I can replace the sine squared of t with y minus 1 squared over 4 equals to 1. And finally, I notice I have a common denominator, which I will now multiply on both sides. Here that eliminates my denominators here, and I am left with a circle. X plus 1 squared plus y minus 1 squared is equal to 4. That's a circle whose center is -1, +1. And with a radius, that's the square root of 4, or in other words, 2. Instead of having to deal with the sine of the arc cosine of whatever and simplifying, by remembering a Pythagorean identity, we can forego all of that and simply end up with, direct substitution without having to deal with the trig functions or the arc functions. If cosine squared of t plus sine squared of t is equal to 1, then these can be directly substituted in, and you end up with this. But now that we know how to graph. It's a circle of radius 2 that has a center of -1, 1. All right, so let's go ahead and graph that. All right, starting from our center, -1, 1. That is not a point on our circle, but now every point on our circle will be 2 steps away from that point. Okay? So 2 steps up would be right there, 2 steps down, 2 steps to the right, and 2 steps to the left. And there we go. There's our graph. It's that circle. Now we still need an orientation, but notice here we have a restriction on the values of t. So let's start with t equals to 0, and then we'll plug in another number, and that'll give us our orientation. It'll tell us whether we're going this way or this way. Note that you may not wish to use 0 and 1 like we did for the previous example, because if you plug in 1, the sine of 1 and the cosine of 1 are a little hard to come by. Yeah? So let's go ahead and try value of t that is a little more friendly to trigonometric functions. Let's do 0 and pi, for example. Okay. Remember, your numbers have to be between 0 and 2 pi anyway. So 0 and pi sound all right. Let's see here. We want t equal to 0. Okay, well then that means your x value. If you plug in 0 right there, the cosine of 0 is 1. 1 times 2 is 2. Minus 1. That's 1. And then if you plug in 0 over here in your equation for y, that's going to give you sine of 0, which is 0, times 2, which is still 0, plus 1, which is 1. Okay, so 1, 1. Oh, that's this point right here. So that's what's going to happen when t is equal to 0. And then when t is equal to pi, well, let's see. Cosine of pi is negative 1. Negative 1 times 2 is negative 2. Minus 1 is negative 3. And then the sine of pi is 0. Times 2 is still 0. Plus 1 is 1. So negative 1, 2, 3, comma 1. Oh, that's this point over here. Okay. Oh, you know what? That is, that's not very helpful. Because here, I'm still not sure if I went from here to here, or if I went from here to here. After all, it's on the exact opposite side. So maybe I should plug in something in between. Let me try pi over 2. Right? I don't know if I went up this way or if I went down this way. So that was unexpected. I didn't know that was going to happen. So let me plug in the third number and see what happens then. Pi over 2. The cosine of pi over 2, that's 0. And then 0 times 2 is still 0. Minus 1 is negative 1. Okay. And then if I plug in pi over 2 over here, sine of pi over 2 is 1. 1 times 2 is 2. Plus 1 is 3. So negative 1, 3. That's negative 1 up by 3. There we go. So here's what happens when t is equal to pi over 2. And now we have a very clear indication of what's happening. 0, pi over 2, and then pi. So our orientation is counterclockwise. We're going this way. Starting from t equals to 0, we're going all the way around back to here. And so there is our result. All right, so let's go ahead and have you give it a try. Take the following parametric equations and go ahead and graph by removing the parameter, by eliminating the parameter. So try the following two. You're going to graph by eliminating the parameter. Don't forget, just because you've eliminated the parameter doesn't mean you don't need the orientation. That's still part of the graph. And go ahead and try two problems here. The first one will be the plane curve where x is equal to 2t minus 4 and y is equal to 4t squared. No restriction on t. T is any number. And then the other one, let's have you try x is equal to 5 times the secant of t, and y is equal to 3 times the tangent of t. Here we are going to have a, oh, actually I take it back. There is no restriction. I was going to say there's a restriction on this one where t is between, no, actually that one is open. So here any values of t are acceptable. So go ahead and give this a try. Pause the video and give yourself what time you need and eliminate the parameter and graph. Once you have both of those, go ahead and unpause the video and we can go through those together. All right, so here we can eliminate our parameter. No trigonometric functions here in our definitions, so we can simply solve for t. It's when you have a trigonometric function that you often wish to rely on some identity. All right, so here we go. I'm going to solve for t on this one. I can do it for this one, but that would give me a plus or minus square root to get rid of that square. And I think I'd probably better off just solving for t over here. It's easier. So I can I can add my 4 to both sides. So that's x plus 4, and then divide by 2. So here that's going to give me t is equal to x plus 4 over 2. And now that, I can plug that in over here. And this will become y equals 4 times x plus 4 over 2 squared. That replaces that t. Notice that when I square 2, that's going to give me 4. And so that 4 will divide into that 4. So really all that you're left with is y equals x plus 4 quantity squared. So that'll be a parabola that's been shifted over to the left by 4 steps. So that we can graph. Normally our parabola would start at the origin and go up this way. That would be y equals x squared. But that plus 4 moves everything to the left 4 steps. So that would mean our vertex is no longer at the origin. It's now 1, 2, 3, 4 steps to the left. Back over here. And now that parabola would be on this side. Note that doesn't tell us anything about the orientation. It only tells us about the path. It only tells us about the points that make up that plane curve. But now to find our orientation, we simply need a couple of values of t. So here let's say t is equal to 0 and t is equal to 1. Those seem simple enough to use. If t is equal to 0, then x is equal to 2 times 0 is 0, minus 4 is a negative 4. And then the y, 0 squared is 0, times 4 is still 0. Okay, so negative 4, 0 is this point right here. It's the vertex. All right, so that's your time equals to 0. And then when t is equal to 1, that's going to be 2 times 1 is 2, minus 4 is negative 2 for my x value. If t is equal to 1 over here, 1 squared is 1, times 4 is 4. So negative 2, positive 4, right up here. And that's going to be what happens when t is equal to 1. So our orientation is from left to right. If we had another curve that looked exactly like this, but the orientation was from right to left, that would be considered a different curve. So if your orientation is backwards, or if your orientation is missing, that is not the correct graph. It has to have this orientation in particular, from left to right. Our other problem here, you'll notice you have a couple of trigonometric functions. So we're going to want to use a trigonometric identity. Just like we have a Pythagorean identity that relates sine and cosine, we have another one that relates secant and tangent. It's secant squared of theta, or in this case t, I suppose, minus tangent squared of theta is equal to 1. So here, recall the other version of the Pythagorean identity. Secant squared of theta minus tangent squared of theta is equal to 1. So we're going to isolate secant of theta, or in this case secant of t, and try to square it. And same thing for this one, we're going to try to isolate tangent of t and then square it. Okay, so here we can isolate secant of t quite simply, dividing by 5. secant of t is equal to x over 5, which means I can square both sides to give me secant squared of t is equal to x over 5 squared. Likewise over here, we can isolate tangent of t by dividing by 3. This will give us tangent of t is equal to y thirds. And then squaring both sides gives us tangent squared of t equals y over 3 squared. But notice now that that is the same as this expression here, secant squared of theta, or t, and that's the same as this expression here, tangent squared of theta, or t. It doesn't matter what variable we have. As long as we have the secant squared of a variable minus the tangent squared of a variable, that's equal to 1. But we can substitute secant squared of the variable by x over 5 squared. Minus, we can substitute the tangent squared of the variable by y over 3 squared. Like that. And that's equal to 1. Here we can actually square everything out to give us x squared over 25 minus y squared over 9 is equal to 1. And that is a hyperbola. So that's a parameterization for a hyperbola. Let's go ahead and graph that now. All right. We have a hyperbola. Note that x is the variable in the numerator of the positive term, which means that our transverse axis will be parallel to the x-axis. So our vertices will be left and right of each other. Notice that our center is at 0, 0, since nothing's being added or subtracted from the x or y variable. So from the center of 0, 0, our vertices are going to be left or right. In other words, our vertices are going to be on the x-axis. Here, the denominator is 25, or in other words, 5 squared, which tells you that you are now traveling 5 units from the center in either direction, and that will give you your vertices. Okay, so here you have 5, 0 and negative 5, 0 as your vertices. This 3 squared tells you that in order to find the asymptotes for your hyperbola from the center, you would go in a direction perpendicular to the transverse axis, in other words, straight up and down, plus or minus 3 units. 1, 2, 3. And so now we can find our asymptotes by forming the box that we get by going up 3, down 3, left 5, and right 5, and then connecting the corners to give us the asymptotes. Notice that without even trying, connecting the corners also has these lines crossed right through the origin, right through the center of your hyperbola. All right, so now we know where our hyperbola is. It starts at this point here, and it's going to follow along its asymptotes. And then the other branch will start from back here and follow along its asymptote as well. Oh, I shouldn't draw those little arrows, though, because we don't know the orientation yet, do we? So let me not draw those little arrows. We'll have to hold off on those until we actually know which direction our hyperbola, in which direction we're following our hyperbola. Okay, so this gives us our path. This tells us where our points for our plane curve are. And we found that by using this Pythagorean identity. But now we need to figure out what the orientation of this is. So what we're going to do is we're going to substitute in some values for t to find our orientation. Now, one thing to note though is we are free to plug in any values of t because we weren't given any restrictions. Well, that's actually not quite true. We weren't given any restrictions to the value of t, but because of how the plane curve is defined, there actually are some restrictions because of the functions that we used. Notice the tangent of t and secant of t. Neither of those are defined when t is equal to pi over 2, or 3 pi over 2, or 5 pi over 2, or in fact negative pi over 2, or negative 3 pi over 2, negative 5 pi over 2. Because after all, tangent of t is sine of t over cosine of t, and secant of t is 1 over cosine of t. They both have a denominator of cosine of t. And that's not going to be defined if cosine of t is equal to 0. So again, these are undefined at pi over 2 and 3 pi over 2 and so forth. So here these are undefined. Secant of t and tangent of t are undefined. For t equals to pi over 2, 3 pi over 2, 5 pi over 2, ... So what that means is that when we choose our values, we need to make sure that we don't choose any of these, because of course our functions are undefined here. Not only that, but we need to choose numbers that are between these two. The reason for that is if there's a discontinuity here, if something's undefined, what will happen is your graph will jump from one place to another. Essentially, okay, everything's nice and continuous, and my function's undefined for that one point. Oh, well then I'm no longer on my graph. Okay, but once I get past that point, I'm going to come back on my graph. But I have no way of knowing where I'm going to come back. Maybe I came back right where I left off, or maybe I'll come back over here, or maybe up there, or maybe over here. So when you do that, when you choose your points, not only can you not choose these, because these would be undefined, but also you need to make sure that you choose things that are between here. So if I choose one point as pi over, let's say I choose pi, and then I choose 3 pi, that's not going to work well. I need to choose things that are within that interval. All right, so let's go ahead and do that. Let's take t to equal to, I'm going to choose 0. So remember this plus or minus, any of these. So I'm going to choose t equals to 0 and pi over 4. Because after all, both 0 and pi over 4 are between negative pi over 2 and positive pi over 2. Okay, so I'm going to go ahead and do that. That's my t, so let's see what x and y are. If I have t is equal to 0, there you go. If t is equal to 0, then I get that the secant of 0, that's equal to 1, times 5 is 5. Okay, so if t is equal to 0, x is 5. And if I have t is equal to 0, plug it in up here, tangent of 0 is 0, times 3. Well, that's still 0. Oh, that's this point right here, 5, 0. So that's going to be what happens when t is equal to 0. All right, let's try pi over 4. Okay, if I take the secant of pi over 4, that's going to be 2 over root 2. And if I multiply by 5, that'll be 10 over root 2. Now if I take the pi over 4 and plug it in here, the tangent of pi over 4, or what is that, 1? It should be 1. 1 times 3 is 3. All right, so 10 divided by root 2, that's not exactly a nice looking number, is it? Let's just give an approximation. After all, we're just looking for more or less where it is on the graph. 10 divided by the square root of 2, that's about 7. So here that's going to be 7 comma 3, more or less. So that's going to be 5, 6, 7 comma 1, 2, 3. So that's going to be at that point right there. Notice that's slightly above where I wanted it to be. Okay, so there we go. There's our point where t is equal to pi over 4. And that does give us our orientation. From 0 to pi over 4, we're going this way, which means that on this part of this, on this branch of the hyperbola, we're going from bottom to top. Okay? Now, if you if you, for example, chose a negative pi over 4, that would be over here. All right, so here's negative pi over 4, 0, pi over 4. We could choose 5. We could choose pi over 3. We could choose numbers that grow and grow and grow, but eventually we would get to a bug on my desk. That was unexpected. We would get to pi over 2. Okay, so at that point, that's undefined, which means that your graph will continue to grow until t is equal to pi over 2, in which case you will not be on your graph anymore. That will just disappear. But then once you get past pi over 2, you'll reappear. I imagine somewhere over here on this part of my graph. Well, let's see. If t is a number that's bigger than pi over 2, let's go with, well, it's got to be bigger than pi over 2, but still less than 3 pi over 2. So let me say pi. Then here's my x and here's my y. Let's see. If t is equal to pi, let's plug it in right here. Secant of pi, that's going to be negative 1. And 5 times negative 1 is negative 5. If I plug in pi in for my y value, if I plug in t is equal to pi to find my y value, the tangent of pi, that's going to give me, what, 0? 0 times 3 is 0. So I have negative 5, 0. That's that point there. So that's what happens when t is equal to pi. Okay? And then let's choose something bigger than pi. But again, you can't get to 3 pi over 2 because that would be discontinuous. So something greater than pi but less than 3 pi over 2. Let's go with 5 pi over 4. That should be okay. Yes, that's fine. So now we're going to have our x value. Okay, well, we're going to come over here and have the secant of that 5 pi over 4. And that would be negative 2 over root 2. And that's getting multiplied by 5. So that'll be negative 10 over root 2. All right, we had negative 2 over root 2, but then times 5. Now I end up with negative 10 over root 2. And then if I take 5 pi over 4 and plug it in over here to find my y, okay, tangent of 5 pi over 4, that is, let's see, tangent of, well, that'll be 1. And 3 times 1 will be 3. So that's going to be negative 10 over root 2, which is about negative 7. And then your y is 3. So negative 5, 6, 7, and up 1, 2, 3. So right about there. And so that's what happens when t is equal to 5 pi over 4. And so we have our orientation from here going up this way. So what happens is as you travel between asymptotes here, if you go from negative pi over 2 to pi over 2, you go up this way. And then when you get past pi over 2, as you hit pi over 2, that's undefined, so you kind of disappear off your graph. But then once you get past pi over 2, you come over here. And as you travel from pi over 2 to 3 pi over 2, you do this. Oh, but once you get to 3 pi over 2, you disappear again. But then when you get past 3 pi over 2, you come back over here. So this kind of does this. Over here, disappear. Over here, disappear. Over here, disappear. Over here, disappear. Over and over again, ad nauseum, forever. But all we see are those two branches. So that is our result. All right. Lastly, for our topic here, we've seen what happens when we're given a parameterization. But how do we find our own? If we're given some equation without a parameter, how do we make our own? How do we introduce those? Well, there are some more advanced ways to do this, but the simplest way is straight up through substitution. For example, here, let's go ahead and write a set of parametric equations. Write a set of parametric equations for, let's go with y equals 4x minus 3. Okay? There are some more advanced ways to do this, especially as your equations become more complicated. However, the simplest way is to simply take your independent variable and call it something. Usually t works. Now you call it t plus 1 or t plus 2 or t minus 7 if you like. But here, the most common one is to simply say x is equal to t. That's a parameterization. But now, what about y? Well, if x is equal to t, you can replace that x with a t. So y is equal to 4t minus 3. And there we go. That's a parameterization. Now, if you use something slightly more complicated than t, that will change your parameterization. So the thing about parametric equations is that they're not unique. I can parameterize this curve several ways. For example, another one would be, let me say instead of t, let's say I'm doing 2t. Let's say x is equal to 2t. Okay, well then y would equal to, this x is being replaced by 2t. So that's 4 times 2t, that's 8t minus 3. And that looks different, but that's still a parametric set of equations. I could say x is equal to 1 minus t, for example. And then I could say, well, that x is going to be replaced by 1 minus t. So that'll be 4 minus 4t. Oh, then I'm subtracting 3. Okay, so 1 minus 4t. And that's another parameterization. And I could keep going. I could use different values for x and find different parameterizations. If you graph all of these, they will all have the same path. They will all give you the same curve or line. What will change is going to be the orientation. These might give you the same curve, but one will orient one way, one will orient the other way, one will travel through the line faster, meaning, you know, if here's 0 and here's 1, for one of these parameterizations, this might be 0 and this might be 1. So you have greater distances between your points. Right? So all of these will give you the same curve, although the parameterization and distance between points will be different for different parameterizations. So just keep that in mind. You might wish to give this a try, and this is about as simple as it looks. Go ahead and give me 2 different parameterizations. Write 2 different parameterizations. For the equation y equals, or let's say x squared minus 4. Okay? Give 2 different parameterizations. Go ahead and pause the video and give yourself whatever time you need. And once you're done, go ahead and unpause and we can finish this off together. Okay, so we have the simplest one is where x is equal to t, in which case y would equal to t squared minus 4. And there we go. That is a parameterization. Now, of course, we can use another parameterization. We can say x is equal to. You probably got this one as one of your 2 because it is the most basic one, and it's the one you will use the most often should you need to parameterize something. However, if that's not the one you wish to use, the other one that you can use, well, there is no other one. You can make any choices you like. Here you can say x is equal to 2t. You can say x is equal to 1 minus t. You can say x is equal to the square root of t plus 5. You could say anything, really. So here I'm going to make a choice just to actually answer my own question. However, there's a good chance that you probably made a different choice, and that's fine. You're not going to have 2 unique answers. If you got one or even both of these parameterizations completely different from the ones I have, you may still be correct. So just keep that in mind. Parameterizations are not unique. So here, just to answer my own question, I'm going to make another choice here, and I'm going to say 2t. I'm going to use that one. All right, well then y is equal to 2t squared. 2t squared minus 4. And if I square 2t, well that's 4t squared minus 4. And there we go. That's another parameterization. And if you have one or both of these, great. And if you have different ones from these, those may be correct as well, as long as you chose one for value for x and then substituted in to find the parameterization for y. And these are the parameterizations for your level curve. And that's it. That brings us to the end of this topic and the end of this section. If there are any questions, comments, or problems, please make a note of those, reach out, and I hope everyone has a nice day.